Alright, in this video we're going to be talking about how to add fractions. If you have not watched some of the videos leading up to this about properties of fractions, it'd be highly recommended because some of this kind of references previous videos. So we need to begin with understanding if we have the problem 2/3 plus 4/3, that we're talking about two segments that are each a length of 1/3. And this we're talking about four segments that are each a length of 1/3. So we have 2 of something and 4 of something, and the 2 of something, each one of those is the same length as the 4 of something here. They're all a length of 1/3. This is 1/3 plus 1/3, or 2/3, plus 4/3. And the associative property of addition says, hey, if you're just adding, then it doesn't really matter how you group things, so we can get rid of these parentheses and say, hey, that's 1, 2, 3, 4, 5, 6, that's 6/3. To kind of remind ourselves of how addition works on the number line, if we have 3 plus 6, well, first of all, it's assumed when we say 3 plus 6 that we mean 3 ones plus 6 ones. So we can simply go 1, 2, 3, that's 3 ones, and then another 6, 1, 2, 3, 4, 5, 6, and we have a total of 9 ones, and this is pretty straightforward. Well, the same logic applies to fractions if the denominator is the same. Hey, okay, we're not talking about ones anymore, we're talking about 1/5. Or the distance of 1 divided into 5 segments. So 1 1/5, 2 1/5, 3 1/5, and then another 6. So we wind up with a total of 9 1/5. And in general, if the denominator of two fractions is the same, then we have some number of 1/b plus another number of 1/b, and we can kind of combine that and say, well, whatever that numerator is in that numerator, that's how many 1/b's we have. So we can just add a plus c over b. And just to kind of illustrate an example of that, if we had 2/3 plus 5/3, well, hey, this 2/3 and we have 5/3, well, that's a total of 7/3, right? And the problem's solved. So let's look at some examples. We have 4/7 and 9/7. Well, that's 13/7. Easy enough. We just add, we go up 4/7 and then another 9/7, and we wind up with 14/7. Same thing here. We have 9/2 and 6/2. Well, okay, go up 9/2 and then another 6, and we wind up with 15/2. The problem occurs when the denominator is not the same. And to kind of illustrate an example that may be a little bit more accessible is if we said Dr. Creef's room was 30 feet, and the wall between her room and Miss Woodard's was a foot, and then Miss Woodard's room was 25 feet, well, we could say, okay, well, that's, let's see, that's 30 plus 1, that's 31 feet to get to here, and then another 25, well, that's going to be 56 feet. And since the 30, the 1, and the 25 are all referencing the same length, it's easy enough to just combine them and say 56 feet. But if I had given you the problem that Dr. Creef's room was 10 yards, and the wall was 12 inches, and Miss Woodard's room was 25 feet, we can't just add these numbers up because they mean different things. 10 yards, well, a yard is a different length than 12 inches. So we can't just add 10 and 12, and I think it's kind of intuitive. You wouldn't say 22 something. You would have to convert to get to the same measurement. And you'd say, well, 10 yards, well, how many feet are in a yard? There's 3. So this must equal 30 feet. And 12 inches, well, there's 12 inches in a foot, so this must equal 1 foot. And now we're talking about the same measurement, the same distance. So 30 and 1 and 25, and we're back to 56 feet. Well, the same concept applies with fractions. 2/3, well, a third is that long, right? A third means divide 1 into 3 segments, so that's 1, 2, 3, and then represent 2 of them. Cool. A fifth is a very different thing. A fifth says we need to divide this into 5 equal segments, so each segment's a different length. So 2/3 and 4/5, those are not equatable. It's apples and oranges. They're representing, say, yards and inches or something. They're 2 different lengths or measurements. So once again, just like with feet and yards, we need to figure out some way to convert them so that we're talking about the same distance. And so let's move on. What we could say, given the cancellation property of fractions, which is in the comparing fractions part 2 video, we know that 2/3, no matter what the coefficient is, if it's the same coefficient for the numerator and denominator, the fraction's still the same. So instead of saying 2 groups of 1 and 3 groups of 1, we could say 2 groups of 5 and 3 groups of 5, and it's still 2/3. And instead of saying 4 over 5, we could say 4 groups of 3 and 5 groups of 3. And it's still a ratio of 4 to 5. It's still the fraction 4 over 5. But if we notice in doing so, we now have kind of created these new fractions. We have 2 times 5, well, that's 10, over 3 times 5, that's 15. And here we've got 4 times 3, well, that's 12, and 5 times 3, that's 15. But notice now we have 10 fifteenths and 12 fifteenths. We're talking about the same unit of length. And therefore, we can now just say, well, that's a total of 22 fifteenths, and the problem is solved. In general, if we add a coefficient of this fraction's denominator, so ay and by, and over here we add a coefficient of if we add a coefficient of this fraction's denominator, which is b, well, then we have yb, right, and xb. Then suddenly we have like denominators. by and yb, well, community property says the order doesn't matter, so these must be the same thing. So we have ay plus xb. And this is our solution. And that's what we just did. This is just an algebraic representation. So let's look at an example again. We've got the same problem, 2 over 3. Well, we said, hey, let's add this denominator's coefficient. So 5 times 3 and 4 times 3. We still have 4 over 5. It's just 4 3s and 5 3s. And now let's add this guy's denominator. We have 2 5s and 3 5s. We haven't changed the value of our fractions, but what we have done is we've enabled ourselves to have like denominators. 5 times 3 and 3 times 5 is the same thing. So we're left with 10 over 15 plus 12 over 15. Well, that's a total of 22 fifteenths, which is what the answer is. So we look at some problems. Let's take a look at another one. Let's come over here. This is a pretty straightforward one. We have 5 1s over 5 1s. And let's bring this denominator over here. We have 1 5 and 4 5s. Well, what does that become? That becomes, well, 5 over 5 plus 20 over 5. And now we can say, okay, well, that's 25 fifths. And I would encourage you to work some of these other problems out. You can see this would be 7 times 3 and 12 times 3, right? 12 3s and 7 3s. I got the 3 from right there. And then let's take this denominator. This is 3 7s and 4 7s. Well, what is 12 times 3? That's 36 over 21. Plus, what's 7 times 4? That's 28 over 21. Well, great. Now we're talking about segments that are each 1/21th of 1 unit. So we have 36 and 26. That comes out to, what, 62? 62 segments that are each a length of 1 over 21. The same concept applies to subtraction, and I won't belabor the point with more examples, but the same thing applies. If we have BD and DB, as long as we keep that cancellation property intact. I'm sorry. It's meant to be a D, and that's a D. And this is CB over DB. Then we have like denominators, and we're just left with AD minus CB, and that's over BD, which I have illustrated here. Thank you so much. This is addition and subtraction of fractions.